Hey everybody, Lars here. You probably notice a little bit different background today because I'm not sitting in my dining room as you're used to seeing. Today I'm sitting in the cave because I had to be here to do some work, so I figured really quick I would bang out this one last video for us. We're just going to talk about data structures really fast. As you've probably gotten the idea, Unit 6 is more of a review and more of exposure, and I want you to see these big main 4 data structures, but we're not going to get into it, and we're not going to get crazy because you need time to do your final project, and I'm getting you this video late, obviously, and the video and everything's going to be due on Monday, so it's not a big deal. I just figured I'd go over things really fast just to have it on video, and so you have more than just one resource. Let's see, do I want to look at stacks? Yes, I want to look at stacks. So as you know, stacks and queues are very closely related, so I usually review them together. A stack is nothing but a PES dispenser. It's a list where when you put something in, it's the next thing out. So if I put it 1 item, 2 item, 3 item, and then I take something out or pop it, I get the 3 item. It's just like a stack of plates or a PES dispenser. And as a data structure, it's useful for incomplete jobs, especially when we do things with operating systems and some other high-level stuff. Because you're in the middle of a job, all of a sudden, I got to go do something. You push what you're doing to the stack, and then you go do something, and then when you pop the stack, what you were doing is right there and ready for you to work. So that's usually in computer science how stacks are utilized, and stacks are utilized as a data structure all over computer science. You cannot get away from them. A queue, on the other hand, is just what you think it would be. It's like a queue in the grocery store. When you go in, you take your place in line, and then slowly but surely the line moves and you come out the other end. Now, those are the 2 data structures, stacks and queues, and classically when you learn computer programming in the 80s and 90s, you would create an array, or in our case a list, and then you would create functions to do the push and to do the pop and to do how big is the stack and other things like that. We have 2 different things going on here. One, we know about object orientation now, so a lot of these data structures lend themselves to object orientation. You want to create an object called a stack or an object called a queue. Now, the second thing, forgive me, it's boiling in here, and I have a cold. I'm a train wreck. Anyway, another feature that we have here is that we're doing it with Python. And Python has a lot of things built in already to work with data structures, so we can utilize these structures without having to create a whole bunch of code ourselves. And as you can see by the code I have here up on the screen, if you want to implement a stack, just grab a list. And basically a push is just like an append, okay? From one end, it puts it in the list on one end, and then if you want to grab what was just put in, you call it a pop. And they already have the function written. So instead of push, say append, and for pop, say pop. Let me run this guy right here so you can see it. And as you can see, as the code runs, I say append test, then append 2, then append test 2. These are all pushes onto the stack. So what's the last thing I pushed? Test 2. So when I look at the stack and I do the first pop, what should I see? I should see test 2, and that's what happens. First, we look at stacks. So the first thing we're going to do is the pop, test 2, and then 2. So test 2, as you can see, was the third thing put in the stack, but it's the first thing that we pop out. 2 is the second thing. So that's how stacks work. Stacks are made so that you can get back what you had just the second before. So the next thing we look at is queues, and queues are just lines. Queues are lines in the grocery store, and the reason we use queues as a data structure, quite simply, is for scheduling. Because what does a queue tell me? It tells me what came in before me and what came in after me. And that sounds incredibly simplistic, but it's useful in a lot of different contexts when it comes to computer programming. Now, in a Python context, we don't even bother with a list anymore. We go to a library, a standard library, which you know about, and we import an object called dqueue, which is just a queue. And it's sitting in the collections library. You can look that up online. And all we do is say queue equals dqueue, and now I have a queue. I use append to do the insert operation. Remember, with a stack, you push and you pop. But with a queue, you insert and then you delete at the end, or you remove, but Python does an append for an insert and a pop left, because you could still do a regular pop, but then you would act as a stack. You don't want to do that. You want to pop on the other side. So you do a pop left. So here we did the same thing we did with the stack. We appended or inserted test, we inserted 2, and then we inserted test 2. Okay? But then when we do our pop left, look what we get now. We get test because it was the first thing in. First thing in is first thing out, FIFO. And we get our 2 in the middle. So that's really all there is about stacks and queues. They seem and are incredibly simple. But you'll find as you get more advanced with your programming that they are incredibly useful for certain circumstances. And now that you know about them, and now that you've done a little code with them, you never have to worry about making them again because they are available in the collections library, and in computer science they're available all over the place. Stacks are available in the Java library. There are stacks you can use in C++. You can use queues anywhere. So all of these things have been implemented because they are mother's milk to a computer programmer. So you know about stacks, you know about queues. We quickly, because I wanted to spend the second half of the unit on linked lists, look at binary trees. But I think I'm going to do binary trees at the end of this video because I'm just going to give it a simple rundown. And I want to look at linked lists really quick now first. A linked list demands a drawing. A linked list is this. Usually when you have a list or an array, wow, that was bad. Usually when you have a list or an array, you have memory that is right next to each other. So you have your first item in here, next item in there, next item in here, blah, 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 down the line. How can I delete this? Look at that. Okay, I don't know if I want to do that. There we go. The secret, as you got from your slides, with a linked list is that we want to create a list where I can put my items anywhere, and we can attach them by telling an item in the list where the next one is. So it introduces the concept of what we in computer science call a node. A node is just something that contains more than one data item but is just a segment of a list. And in our case with a linked list, our node contains our data item, boop, and then what we would call a pointer, in this case it's just going to be the name of a variable, that points to the next item in the list. And as you've seen in the slides, in this fashion, I can have nodes all over my memory. But because I always point to the next item in the list, I can maintain that list and keep it in order. Because they don't have to be next to each other now. I'm telling you where the next item is, and then we can go to that next item in the list. Now, a node is one thing, but when I create a linked list, that's basically the higher level thing that keeps track of all the nodes. So you'll notice the node has the data, and the node has the section in it that points to the next item. What does the linked list have? The linked list really only has two things. The linked list has what's called the head. Oh, I am not going to be able to draw this very well. It has the head, and basically it has the size. So what does a linked list do? What does the head point to? The head points to the node at the front of the list. That's all it does. It just points to that one item that's right at the beginning of the list. And then the size will get clicked every time I add a new node, so I'll know how many items are in my list, and this comes in handy later down the line. So when we have a fully realized linked list, we're going to have data item, the head points to this, and then this points to the next item. And then I'll have my next item right here. And I'll have data in there, and then this will point to the next node, and so on down the line. Now, these items don't have to be next to each other in memory. They can be wherever you want in memory. This looks like a 5-year-old drew it. Look at that drawing. So that's how linked lists work. And then when you insert, all you're really doing is adding something to the head of the list. Okay? You're telling it what head used to point to, now put in here, so it'll point to that. And change head. Let's see how well this eraser works. Not sure, shabby. and then change head to this. That's all you're doing, those two things. When you insert into a linked list, you put it in the front here. You change this memory location to point to this, which used to be head, so it's easy. You just take, this is next node, and you just take next node and make it equal to what the head was. And then you point head towards that, and that's it. That's all. And then we can add more items down the line. Now, I don't get into it because it's a short 2-week look at a whole bunch of data structures. It's a data structure survey. If we wanted to get into linked lists, we could get into linked lists for probably a month. Because what would happen then is you would say, okay, how do I delete an item from my linked list? And you would come here and say, okay, if I want to get rid of this item, I have to tell this to point to this now and get rid of this, and then I'm done. Okay? So then that would be a delete in a linked list context. And then, as some of you know, I would go into doubly linked lists. Because if you have a linked list and you go down the line, there's no real way to go backwards when you have a singly linked list. But if I had a double linked list, well, then I'd be in good shape because then I would know where I came from and not just where I'm going. So, this is messy. Can I just get a new to get rid of that? No, don't save anything. Hey, there's my new. All right, we'll come back to that. So here, if I'm not mistaken, okay, well, that's because I'm not using it. Let me go grab, what did I call it? Use LL? Yes, use linked list. And I don't have my get num because that's your homework. So I'm just going to delete that, save this, and run it. And as we can see, that's the linked list. Let's see, grab this. No, not like that. So like that, like that, like these. As you can see, I grab my list. It's just a linked list. And then I insert the node. You see how I create an object called node. You see here, I don't have one class here. I have two classes. I have one that defines a node, the data, and the pointer to the next object. And then I have my linked list. And my linked list, like we just said, keeps the head and keeps the size. That's it. Linked list is a way to organize our nodes. Excuse my cough. I cannot get rid of this cold. So that's basically it. The linked list has the two data items, the head and the size of the beast, and the node just keeps the data and points to the next thing in the list. So when I use it here, I create a node. I say for the data item, make it Lars, and it has a default of none for the next pointer, as you can see up here, because we'll assign it later when we get to linked list. Then I insert it in my linked list, and when I do the insert, I basically have head point to it, and I click my counter, and that's it. And that's how I add it to the list. So I go down the line, I add 1, I add 2, then I do a get size, it prints 2, I add Michael, then I do a get size, I see 3, and then I add Abby. You'll notice as these things are being added, they're being put at the front of the list. Okay? So if I want my second item, I'm going to get Michael as my second item. As you know, for the homework, I want you to write a method that basically will print out an item in the list that corresponds to a number you give it. So if I give it a 2, I want to print the second item in the list. In this case, that would be Michael. I am not going to sit here and do that assignment for you. That is why it is called homework. But I thought I might do this. You see how I have the print LL here that prints the node? I can do something like this. Let's say C equals 0. And while my node C plus equals 1, print my node data C. So let me run that. Should get nothing because that's the class. Now when I use LLL, do I do a print LL? I do a print LL. Save, go. And it printed nothing. Great, thank you. Why did it do that? Print LL. Am I using, maybe I'm using the homework that I wrote for you guys. Use linked list. Don't use linked list, get none. And there we go. Okay. When I give you guys homework, I try to be fair, so I do it myself first. So I had done that already. Somewhere deep buried in my laptop is the function that does your homework, and that's what I was using. So when I altered linked list and changed it here, the change didn't take because this code was using something else. But now it's not, and now it works. So as you can see, just by doing those two simple changes, well, three simple changes because I printed it, but I just added a counter to the print LL, and now next to it, it's giving me the number that it is in the list. Knowing how to do something like that may be helpful to you. Yes, 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 yes. All right. All that done, and I gave you all this code. All this code is up there on the in the resources folder for you to use, so you should be good to go as far as that's concerned. The last thing I'm going to do before we get to the fun and wonderful announcements / final comment section is we'll look at binary trees. Now that I showed you what a node is, in a binary tree context, a node has three parts. And what a node is in a binary tree context is this points to what we would call a left node or a left leaf. Then this memory location prints to a right leaf, and this has the data location in it. So that's what a node looks like. And a binary tree, usually when it's drawn, looks something like this. So as you can see, each node has a payload or a data item and then pointers in two different directions, right and left. You don't have to point to anything. In this case, we're pointing at nothing. Okay? In this case, we're pointing at two. Let me just do this. In this case, we're only pointing at one, the right side. Now, you might be saying, well, why am I organizing my data in this way? I said it a couple of units in the past. I'll say it again now. This lends itself to being attacked recursively. Because at the end of the day, what do I have at my binary tree? Two binary trees. What do I have here? Two binary trees, another binary tree. So it lends itself to being looked at recursively. Okay, get left. I went left. Is there another left to go to? Yes. Then call yourself again. Okay, is there another left? Yes. Then call yourself again. It's good for recursion, and if you get more into binary trees, which you may do when you're doing your data structures and algorithms class next semester, I hope a lot of you guys are taking that because that should be cool. You're going to get more into this stuff where you're going to say, okay, I can do postfix order and order my data this way, or I can do infix and order my data this way, and then I can traverse my tree in a certain way where I get my data in different orders, and it's very useful for sorting and very useful for searching. You learned a little bit about the searching when we did binary search, but you can set things up in a binary tree so that you can search for things very quickly. So that's all binary trees are about. But when after I wanted to show you what a node was with linked list before I really came here and showed you about binary trees. But that's basically all you need to know or think about for now as far as binary trees are concerned. When you get there in your next course, you will get much more complicated, okay? That's it. I mean, those are the four major data structures I wanted you to see in this small 2-week unit. And I know you're working on your final project, so I kept it light. This is more of an exposure to these data structures to see what they can do and a little bit to whet your appetite for the next level. Because classically, in a computer science education sequence, you would do an intro to programming or an intro to computer science, and you would get pretty much what you've gotten, only you would hit sorting and searching and recursion and big O a little more heavily in a computer science context. But then the second course that you take in a sequence is data structures. And that's what you get. You get stacks, you get queues, you get linked lists, you get binary trees, and you also might get some more complicated things. You'll learn about things called hash tables and some other things along those lines. But for the most part, that's data structures. And that's when the light bulbs go off in your head. That's when you say, aha, now I'm getting this computer science thing. It's about organizing my data so these time-tested, efficient algorithms work on it. And then when you see that happening, you're like, oh, now I get it. Now I know why we're organizing things the way we're organizing them. And when you steep in it for a while and you learn more about these things, you realize that this is how we problem solve with discrete mathematics. This is how we problem solve when we have to take things step by step by step by step. So That's data structures. That's my story. I'm going to stick to it. All right. This is going to be your last video. I'm kind of sad. I spent all semester talking about the Mets and talking about Rutgers football and talking about all these specific things. So I just realized I've painted myself into a corner. I can't reuse these videos. I'm going to have to do a whole new set of videos in the spring, but I think that's better anyway. So at the end of the day, I think I'm going to create a web page that organizes all of our videos and all of our slides, because I'm going to leave them online too, I believe. And then I'll send you that link. So anytime you want to go back and relive the greatest hits of Python methodologies for data science, you can do it. And I hope you do. I hope you continue to use all of this stuff as a resource. And I hope that you got computer programming and using Python framed properly, so that you can say, okay, now I have a good base, I have a good foundation, blah, now I can go out and use Pygame to make video games, or I can use Django to make websites, or I can do all of the things that you guys want to do as far as computer programming is concerned. All right, announcements. We're crunch time, man. Monday is going to be the quiz. It will not be backbreaking. I want you to concentrate on your final projects. Please go put something in the forum. Just a quick review, what you liked about the course, what you didn't like about the course. You don't have to write 3 paragraphs. You don't have to make yourself crazy. Just get in there and be heard. That's all I want. Programming assignments due Monday night. Please try to be on time. Eric and I are going to be grading those assignments Tuesday evening. So if you need a little extra time, you know me. I'm not a big stickler on these deadlines, but this time I kind of have to be, because Eric and I have our lives planned out for the next 2 weeks. We have to grade Tuesday night, because if we don't grade Tuesday night, we're going to get thrown off schedule, and then we can't get to your final projects on Friday night, which is when we think we're going to be grading your final projects. So, Unit 6 quiz, Monday. Assignments, and they are not hard. There's 6 lines of code for each one. Monday night as well. If you drip into Tuesday, it is not the end of the world, okay? Final projects, midnight Wednesday. Please, 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 please keep to that, because Eric and I have to get them in, make sure everything is cool, get them in a state where we know we're going to be able to run everything, and then Friday night we're going to basically barricade ourselves inside a lab and grade until there's nothing else to grade. So we definitely need that the Wednesday night. If you drip into Thursday AM, maybe you'll be okay. But you shouldn't have to, because you got an extra time, a lot of time to work on a final project. And then that's going to be it. Hopefully Eric and I will get things looked at, graded, and whipped up Friday night. Then Saturday I will post grades, and then hopefully you'll have your grades, you know, the minute they're available. I don't know if you have to wait till the end of exams or whether they'll pop up before that. But everybody's doing great. I think it's wonderful. Everybody, so many people have availed themselves of the extra credit programs. Everybody's doing a great job. You guys did a great job, not a good job, a great job with the card class. I cannot tell you how pleasantly surprised I was with that, because I know, because I did it, I didn't give you a lot of feedback with that. You got thrown into the deep end, and you all managed to swim. So I thought that was wonderful. That was an incredibly pleasant surprise. I'm tempted to do a video to show you how I did it, because my version was super simple. But still, you could play acey-deucey with it, and you could play blackjack with it. But I'm holding back because I think I'm going to use this again next semester. See, that's the problem with these videos, is that every time I do a big explanation, I can't really do it again. Like FizzBuzz. I don't know if I'm going to be able to spring FizzBuzz on the spring semester students, because there's video already on it, and somebody may go look at that video. Same with the rainfall problem. Same with Euler 6. Euler 6, I never went and told you guys. You're not really supposed to tell people how you solve Euler problems. I called it Euler, because then people will cheat and just go get the points and do it. So when I put up that video solving Euler 6, it wasn't really a good thing to do. And I said, oh, we'll do more Euler problems, blah, blah, blah. I can't really do that, because then you're showing people how to do them, and then it defeats the purpose. When somebody brand new gets to Euler, they shouldn't be able to go to Stack Overflow or some blog or YouTube and all of a sudden have somebody else solve it for them. The idea is to solve them yourself. So that was a bad thing at the end of the day. It wasn't a bad thing, because it's a simple one. You don't need a video to learn how to solve that. So Monday, quiz. Assignment Unit 6, do a forum post. Done. Wednesday, final projects. Get me the code, get me that demonstration PowerPoint, YouTube video, or whatever, and that's going to be it. That's done. It's the end of the semester. I have nothing up my sleeves and nothing in my hands. All right? So this was fun. This was definitely very fun. I want to thank you guys because you guys did a great job. It was wonderful engaging with you guys, and I think if you put your minds to it, you are all going to make wonderful programmers going forward. All right? Thanks a lot, and I am out of here. You be good now. Bye-bye.